Hello there, Mr. Sutton bringing you this lesson on Taylor series. Now we've already been doing Taylor series, but the focus of this lesson is to construct Taylor series that are not centered at x equals 0. For this lesson, we're just going to dive right into the first problem because you already know most of what you need for these. So let's start by finding the first three non-zero terms and general term of a Taylor series for e to the x at x equals 2. So pretty much everything is the same as what you've done before, except now we have x equals 2 instead of x equals 0. So we're going to need a more general formula than the one we've been using. So here is a new shiny formula. This is the nth term of a Taylor series formula at x equals a, where a can be anything including 0. So we're still going to have a derivative, but this time we're going to have the nth derivative at a. We're going to have x minus a to the nth power. We're still going to have n factorial. So we still have n factorial, nth derivative, nth power, but now we're doing x minus a and a derivative. So for example, for the series at x equals 2, we're going to need f of 2 instead of f of a, plus f prime of 2 times x minus 2, and then we're going to have f double prime of 2 over 2 factorial times x minus 2 squared. And in general, because we want a general term as well, we're going to have this stuff right here with 2 instead of a. All right, so pause the video and see if you can make this adjustment to figure out the series at x equals 2 for e to the x. To do this with e to the x now, you're going to need to know f of 2, which is just e squared. You're also going to need f prime at 2. But the good news is f prime of 2, f double prime of 2, in fact, and the nth derivative at 2 for e to the x, since it's always just e to the x, all of those are going to be the same thing. They're all going to be just e to the x with 2 plugged in, or e squared, just like f of 2. So let's go ahead now and build that series. So we've got e squared for f of 2, plus e squared x minus 2, plus e squared x minus 2 squared over 2 factorial. And this is the first three non-zero terms. So now all we need is e squared x minus 2 to the n over n factorial. And there it is. So you might be wondering throughout this whole process, why couldn't we just substitute x minus a, in this case x minus 2, into the Maclaurin series for e to the x or anything else like that? And the reason we can't just do that is that if you're substituting into a Maclaurin series, whatever you get by transforming a Maclaurin series is still going to have a center of x equals 0, because the Maclaurin series was centered at x equals 0, and nothing is going to change that. The only way to move the center is you're going to have to recalculate all the derivatives at the new center. The idea of a series in general is that you have perfect information at whatever the center is for the function value and all the derivatives. So move the center, do the derivatives over, which means you're always going to have to build these general Taylor series from scratch. For this next example, they want the second order Taylor polynomial for this f of x function at x equals 1. And the interesting thing about this one, if you look at the original function, it's also a polynomial. So yes, we can approximate one polynomial with another. The one that we're doing here is going to have a lower degree, but it's still going to be a polynomial. So pause the video and make it happen. All right, so first we need f of 1. That's going to be 2 times 1 minus 3 times 1, essentially. 1's nice to plug in here. So that's negative 1 for that function value. Next, we need f prime of 1. Derivative, we're going to have 10x to the 4th minus 12x to the 3rd, evaluated at 1. Plugging in 1, this is just going to be 10 minus 12, so negative 2. And then since they want second order, we need the second derivative. That's going to be 40x cubed minus 36x squared, evaluated at 1. So that's 40 minus 36, which is 4. Plugging it all in, we have our f of 1 here, which is negative 1. And then we've got f prime of 1, so negative 2, times x minus 1, followed by, now we're going to have f double prime over 2 factorial, so 4 times x minus 2 squared, or x minus 1 squared, rather, over 2 factorial. So that's our polynomial to approximate this first one. Now I'll just show you this on a grapher. So I've graphed my original polynomial, and here's my approximation polynomial, my Taylor polynomial. I made my window 0 to 2, and let me do a zoom fit just to show you this. So here, between 0 and 2 is the original polynomial, just a piece of it. And here's our approximation polynomial, which seems to be a little bit off, but then is very close near that center. And then it veers off again. But at least we have accuracy near that center of x equals 1. We're going to do one more problem. Let's say that f is a function with all these function values and derivatives. We want the third order Taylor polynomial at x equals 1 and approximate f of 1.2. Pause the video, give it a shot. All right, so this one, we don't really have to do any calculation. It's just plugging things into our formula. So we should have f of 1, which is 4, and then f prime of 1 times x minus the center 1. So this is going to be negative parentheses x minus 1. Next, we've got plus, let's see, this will be 3x minus 1 squared over 2 factorial. And finally, we'll have plus 2 times x minus 1 cubed over 3 factorial. So if we want to approximate f of 1.2 with this, we just have to plug 1.2 into p sub 3 here. And I'm going to write approximately equals, because that's what this is. And now we can just do the rest on the calculator. So I've got this thing plugged into my y1 now, and you might notice that I'm not simplifying this at all. I'm not going to bother unless there's really something else I need to do with it that requires simplifying. So let me quit out and let me do alpha trace y1. We're just plugging in 1.2, and that comes out to about 3.863, and that'll do it. So at this point, you can now build a Taylor series out of any function at any center. Just remember, with great power comes great responsibility. Till next time, Mr. Sutton signing off.